Hello, and welcome to my research talk on verified substitution redundancy checking. This is a repeat of a research talk that I gave for FMCAD 2024 in Prague, and this is work that I've done with my advisors in Rheinvilla and Jeremy Abigad here at Carnegie Mellon University. Stat solving is a crucial research tool that is becoming increasingly used in both industry and academia. For a few examples, Keller's conjecture was resolved with the use of stat solvers. This is a problem on the phase sharing of n-dimensional hypercubes as n increases, or the number of dimensions increases. And the conjecture was that certain phase sharing tilings did or did not exist for various dimensions. And the last open case was resolved by reducing this problem to a finite graph search, which was then resolved with stat solvers. More recently, my lab resolved a variant of the happy ending problem. Here, the problem concerned how many points in the plane are needed before you force certain substructures, and in particular, having empty n-gons, convex n-gons in the plane. And finally, in industry, stat solving technology is being used every day. For example, in AWS, there's a service called Zelkova, which fields over 1 billion SMT queries a day, where users can determine if their security policies are secure or their security policies are not open to the internet. And Zelkova uses SMT to resolve these queries and give customer guarantees that their security policies are correct. One of the selling points of stat solving is that it's trustworthy, and the workflow looks something like this. You have a formula F that you give to a stat solver, and if the solver finds a solution, then the solution is reported, and you can check that the truth assignment satisfies all the constraints of the formula. But if the stat solver says there are no solutions, then it can produce a proof, which is then checked by a separate tool called a proof checker, which takes in both this proof and the formula and checks that there are indeed no satisfying assignments to the formula. The de facto standard is to use a proof format called DRAT. DRAT stands for deletion reverse asymmetric tautology. Stat solvers produce proofs in this format, and then a DRAT checker checks and ensures that there are no satisfying assignments to the formula. However, to implement a DRAT checker, you need to perform a fair bit of proof search. You need to look for unit clauses in a formula that are implied by certain other clauses. And performing this proof search is non-trivial. It means that you have to trust that the DRAT checker is implemented correctly. And so a format called LRAT was developed to solve this problem. LRAT includes those unit propagation proof search hints, and thus, if you produce an LRAT annotated DRAT proof, you can give that to an LRAT checker, which is a much smaller, simpler piece of software that can be formally verified. And thus, your level of trust can rest in the piece of software that's verifying the checker rather than the checker itself containing bugs. So this is all well and good, but DRAT is somewhat limited in what it can express. It's useful for a wide variety of purposes, but sometimes proofs can get quite large. And so a different format called DPR was developed. DPR stands for deletion propagation redundancy, and this is a superset of RAT. And so all DRAT proofs are DPR proofs, but DPR proofs also include more expressive clauses, so these proofs can be small. And so the workflow looks very much the same. It's just everywhere you see DRAT and LRAT, you replace it with DPR and LPR. Moving to a stronger proof system, a more expressive proof system, can have some benefits. In particular, in the 2023 SAT competition, the 2nd and 8th place finishers used PR reasoning in either their pre-processing or in-processing. And so you get some competitive edge by using a stronger proof system, both inside the solver and when you start to output proofs to be checked. So the hope is the stronger the proof system, the more effective solvers can be, or definitely the smaller your proofs can be. And so in particular, our talk is going to be looking at a new proof system called DSR and LSR, standing for deletion or linear substitution redundancy, which replaces DPR and LPR everywhere with DSR and LSR. So the workflow is the same, but we're using a stronger, more expressive proof system, and we're going to demonstrate that you can do proof checking in the system, and these proofs can be asymptotically small. So SR admits short proofs. We have in our paper 3 examples. We have the pigeonhole problem. If you produce a proof for this problem using only resolution steps, it takes exponential. But if you use PR, you only need a cubic number of additional clauses with respect to the number of poles. And then if you use SR, you only need O of n squared. So you have an asymptotic savings if you move to SR. There's a certain class of formulas called Chaitin formulas. These encode properties of graphs called expander graphs. And so if you use resolution proofs to show that a graph is an expander, you need an exponential number of clauses. For PR, you need polynomial, but for SR, you only need linear in the number of edges of the graph. Finally, if you want to do stat solving on Ramsey graphs to show a contradiction, you need 1 billion proof steps for R44. For PR, you need 400,000 proof steps, and for SR, you only need 38. So there's clearly some additional strength that you get from SR. Our talk will focus on these. So our contributions in this work, we have handcrafted proofs for these three example problems that I've shown. We produced a tool called SR to DRAT, where if you have an SR proof but you don't trust the SR proof checking system, you can translate SR proofs into DRAT and use your DRAT checking infrastructure. But we also have SR proof checking tools. We have DSR trim, which is this unverified, non-trivial proof search piece of software that will do the unit propagation and labeling on DSR proofs. And then LSR check, which is an unverified LSR checker. Both of these tools are written in C. And finally, we have an LSR checker written in Lean. This checker is verified, and as we will see, it is competitive with other verified proof checkers, other similar proof checkers. So, taking a step back, how do we write an unsat proof? Well, you have to write down the clauses that you want to add to the formula in some order. And the hope is by the end you derive the empty clause. When you add the empty clause to the formula, the empty clause is by definition unsatisfiable. So if you show somehow that adding the empty clause doesn't affect the satisfiability of the formula that has come before it, then certainly the formula that has come before it is unsatisfiable as well. So if you were to do this using the resolution proof system, which is pretty popular, it would look maybe something like this. The formula clauses I've written in blue, the additional clauses I've written in red. So here we have two formula clauses, x3 or x4, as well as not x3 or x4. Using resolution, you pick some variable to resolve against. You have an appearance of that literal in one clause and the negation in the other, and then you sort of append all of the other literals together. So here, if we resolve on x3, we append x4 and x4 together to get x4, and thus we have our first resolution clause. If we have a different formula clause, not x4, then we can resolve against those to get the empty clause. And thus we have an unsatisfiability proof in the resolution proof system. We first add x4, and then we add the empty clause. DRAT, DPR, and DSR are all clausal proof systems, which means that the way we go about adding clauses is slightly different. Instead, we add redundant clauses. And these clauses are clauses that do not affect the satisfiability of the formula when added. In other words, F and C are equisatisfiable. So the way that these proofs are structured is you have a list of these clauses that you'd like to add in order, and the hope is that the last clause is the empty clause. First, you show that F is equisatisfiable to F and the first clause, and then you show that that formula is equisatisfiable to that plus the second clause, and so on until you've added the empty clause. And each of these steps can be supported by a witness to help the proof checker show that the clause is indeed redundant. So what does a redundancy proof look like? So here is the formal syntax for how to show equisatisfiability. You want to say on the left-hand side, there exists some truth assignment tau that satisfies the formula F, if and only if there exists a truth assignment tau, not necessarily the same one, that satisfies F and C. The forward direction is, or the reverse direction is trivial, because if you have a truth assignment satisfying F and C, then certainly you have one satisfying F. So these redundancy proofs are left to the forward direction only. And a proof sketch in the abstract would look something like this. Assume that we do have a truth assignment tau that satisfies F. Perhaps we really want that truth assignment to satisfy C. So case 1, tau satisfies C, and we'd be done. But the world isn't so nice. Sometimes we are in case 2, where tau does not satisfy C. And so one question that we can ask is, how can we repair the assignment tau that we have assumed exists, such that we can then satisfy C, but also maintain the satisfiability or the satisfaction of F? And so you might try something like this. So here's a reconstruction of the picture that we had in case 2 on the previous slide. We have tau satisfying every clause in the formula F in purple off to the side, and this is noted with at least one white arrow in each clause. But the candidate redundant clause that we want to add in red here has no literal satisfy. So perhaps we choose a literal in that clause C and we flip it to true in tau, but doing so might unsatisfy a clause in F, so this is bad. So maybe we try a different literal, but we falsify a different clause. We try a different literal, we falsify a different clause. So maybe just flipping one literal at a time doesn't get us what we want. And so one question we can ask is, what kinds of repairs are allowed when we're trying to satisfy C, but also trying to keep F satisfied? And then how do we specify this repair in the proof system? As it turns out, the DRAP proof system makes it so that you can specify one literal inside of this redundant clause here. DPR allows you to specify any subset of literals to set to true or false, and DSR allows you to specify substitutions. We'll see what those mean in a little bit. So for an example, to motivate why we want substitutions in substitution redundancy, we're going to run through a quick example of an SR proof in Pigeonhole. So here we have 5 pigeons, and we want to fit them in 4 holes such that each pigeon has its own hole. This is an unsatisfiable problem because 2 pigeons will have to share a hole. So here we can represent this problem in Boolean logic by having a variable for each pigeon and hole combination. So here we have a grid of 20 variables representing any pigeon going in any hole. So for example, if we put pigeon 1 in hole 2, we would set that variable to true. If we set if we do set pigeon 1 in hole 2, then we can derive through some encoding of this formula that hole 2 can't have any other pigeon in it, so we could set all of those other variables to false. For another example, we could fit pigeon 3 in hole 1 and set all of the other pigeon variables for that hole to false as well. So proof of unsatisfiability for this problem might look something like this. We would want to derive that pigeon 1 does not go in hole 4, represented by not P14, and setting this variable to false. So we can proceed by this case 1, case 2 procedure that we had on the previous slide, where we assume, for the sake of contradiction, that we have some truth assignment that satisfies the encoding of this problem in propositional logic, but we are in case 2, it does place pigeon 1 in hole 4. So this is why we have this faded green line from P1 to H4. So what can we do? We know that the problem has been satisfied and no other pigeon is going to be in hole 4, so maybe we say that pigeon 3 is in hole 1. It would be quite nice if we could just swap the 2 pigeons, indicated by these faded green lines here. We know that pigeon 3 cannot share hole 1 with any other pigeon, so if we just swap the 2, then we can satisfy the additional constraint that pigeon 1 is not in hole 4 while keeping all other constraints in the problem satisfied. And so this swapping of the pigeons is described by this substitution here down at the bottom, where P14 is set to false, P34 is set to true. We're physically placing pigeon 3 in hole 4 and disallowing pigeon 1 going in hole 4. And then we swap the truth values of every other pigeon variable associated with pigeon 1 and 3. We can do this same procedure, running down the list of pigeons here, so we can derive pigeon 2 is not in hole 4, pigeon 3 is not in hole 4, and pigeon 4 is not in hole 4. At this point, we can derive that pigeon 5 does go in hole 4. From there, pigeon 5 can't be in any of the other holes. And then we have reduced this problem to the pigeonhole problem of one smaller pigeon hole. And so we just recursively apply this procedure until we get contradiction, either when we have 2 pigeons in one hole or 1 pigeon in 0 holes. And so the syntax for this rule that we want to apply when doing the substitution redundancy check is described here. So here on the left-hand side, we have F and not C. This is the case 2 logic. We've assumed for the sake of contradiction that C is not satisfied. And if C is not satisfied, the negation of C must be satisfied by some truth assignment. And we want to show that that new formula, it entails the formula F and C underneath this substitution sigma that we've been given. And so this, you can think of this as any truth assignment that we've been given that satisfies F, but it doesn't satisfy C, should satisfy F and C when repaired underneath the substitution sigma. Another note is this turnstile that's in the middle is unit propagation. This allows us to efficiently check this, but in general this could be normal entailment. Alright, so as an aside about this unit propagation thing, if you haven't seen this before, it's a relatively simple procedure. Basically, unit propagation iterates on a partial truth assignment until you have fixed point, where you add in unit clauses and you set unit literals that are implied by the units that you have seen before. So here is an example. We have tau that's currently empty, and we have some clauses off to the side. You'll note that we have a unit clause not x3, which means that if we were to satisfy all of these clauses, we must set x3 to false, or not x3 to true. So we must have this this white arrow here, and we must set x3 to false. So we can propagate this information into other occurrences of x3 and not x3. So we have false x3 in this other clause here, which means not x2 must be true. We set x2 to false. We do this thing again, we see that not x1 must be true, meaning x1 is false, and then we reach contradiction in the final clause because both of those literals are false and they were implied by the units that came before. So this formula, or the set of clauses, is unsatisfiable, and we can show this under unit propagation. And unit propagation is efficient to implement both with and without these hints that are in the proof format. You can use these things called watch pointers to efficiently check when a clause becomes unit under a partial assignment. So that is why we use this unit propagation turnstile instead of entailment in this redundancy check here. Okay, so let's take a look at some SR proof checking. How might this check go algorithmically? Well, first we want to determine if normal unit propagation entailment applies, which means showing that F and not C implies the unit or the empty clause under unit propagation. For now, we're assuming that sigma satisfies the candidate redundant clause C, but in general you don't need to have this assumption, you just need to show the check that we had on the previous slides. Okay, so perform unit propagation into a conflict. If one is reached, you're very happy. If not, you must continue on into the SR redundancy check. So next step is determine if F and not C unit propagation entails F when mapped underneath this substitution sigma. If you didn't have this assumption that's in the top right, then you would have to show F and C when mapped under this, this sigma is entailed. So for each reduced clause D inside of this mapped formula F, determine if F and not C and not D implies the empty clause. This is basically assumed for sake of contradiction proof. You're trying to check if assuming the negation of D causes a conflict. And if it does, then D must be in unit propagation entailed by the formula F and not C. Okay, so we have implemented this algorithmic procedure inside of our verified lean LSR checker. It took about 8,000 lines of code and proofs to write down and verify this. It took 4 person-months to complete. Most of the time was spent fiddling around with getting some performance out of the parser and looping across these arrays, because lean's default or idiomatic way of doing things is not necessarily the fastest, and then reconciling that with how to prove that these alternate ways of looping across these arrays is correct. Then finally, we implement some common stat tricks. In particular, we implemented a form of timestamping, whereby when you start recording these unit clauses or unit literals during these redundancy checks, rather than undoing the set of units that you have derived when you're done with a particular check, you can instead increment some global timestamp to clear out those values very quickly. So we implemented this common trick inside of Lean. However, this did make the formalization more complicated, so there was a bit of trade-off here. So we implemented and verified this thing, but one question is it fast? And the answer is pretty much. We have some experimental evidence to show you. First experiment that we ran is to see whether the Lean checker is comparable to other verified checkers. This is sort of a good baseline because usually having verified software means sacrificing some performance that you would get from using unverified low-level code. And so if we perform well against other verified checkers, then that means that our Lean verification is on par with what other people are doing, perhaps in other theorem provers or other systems. So here on this plot, we have depicted on the x-axis the runtime for a verified checker called cake LPR, which is verified to check LRAT and LPR proof files. And then on the y-axis, we have our verified Lean SR checker. In the middle of this plot, we have a dotted red line. Anything that lies below the red line indicates that our verified Lean code was faster. Anything above the red line means that cake LPR was faster. And each diamond in the plot indicates one proof that was run on both checkers. And the axes for this plot is log-log. And you'll notice that most of the proofs lie along this red dotted line. As the proofs tend to get longer, our Lean checker is a little faster. You also notice that there's this little curve, especially with the green proof instances off to the left. This is due to Lean having to run some amount of startup code when it starts, even in the compiled binary. And so for these proofs that take 0.1 seconds to run, it appears that cake LPR is much faster than our Lean checker, but in reality, these proofs don't take too much to check. For those proofs that take longer than a second, the runtime is extremely comparable. So experiment 1 is a success. Our verified checker compares well against other verified checkers. Experiment 2, does using SR proofs at all improve your performance? And the answer is yes. Here on the left plot indicates the size of the proofs. The y-axis is the size of the SR proof when labeled with hints, and the x-axis is the size of the same proof when run through the SR to DRAT system to convert the proof into DRAT, and then hinted with hints added, so now it's an LRAT proof. And you'll see that anything that lies below the line indicates that the SR proof is smaller, and anything that is along the dotted black line indicates that the proof is 10 times smaller. And this plot is indicating both proof size and number of proof lines. The right plot is our verified Lean checker running against cake LPR on the converted LRAT proofs. The y-axis is our checker on the SR proofs. The x-axis is cake LPR on the converted LRAT proofs. And once again, you'll see that anything that lies below the red dotted line indicates that our Lean checker was faster. And indeed, for most of the proofs that take longer than a second, our Lean checker was faster. So if your problem can benefit from using SR, you will get both size savings and runtime savings. And finally, we wanted to see how much of an overhead we had when we ran our verified checker against an unverified checker written in C. So once again, we have our Lean checker on the y-axis and our unverified checker on the x-axis. And by and large, we have about a 10 times slowdown when compared against the C checker. Most of the slowdown is just due to the fact that Lean operates largely in a functional way, and so it has to very carefully monitor if things are being accessed linearly, the reference count is 1. It has to box and unbox a lot of structures that you would just have direct access to in C. There's also about a 10 to 15% slowdown, or 10 to 15% of the runtime is spent in Lean checker doing just parsing. We're currently working on getting the parsing code set up. But suffice to say, 10 times overhead is not that bad. The standard for these sorts of things is about 3 to 5 times, but with a little bit of work, we can probably bring this overhead down even more. Okay, so future work that we have for this line of work into SR proof checking. One line of work is automatic SR symmetry breaking. So in this talk, we focused on proofs of unsatisfiability where you add redundant clauses until you reach the empty clause. But you can also use this technique to apply symmetry breaking. You take some formula, you add some clauses that break symmetries, and you show that each clause that you add obeys some remapping of the variables such that you're picking a canonical one or the lexicographically smaller one. And if all you do is additions, then at the very end, the formula with the additions is equisatisfiable to the original formula. And so this way you don't have to go through the trouble of writing down a formal proof that the clauses that you've added really do break symmetries. You can just use the SR proof checking infrastructure that we have. We do want faster proof checking tools. There's plenty of work to be done on the lean checker to make its parser faster, to change the underlying representation, so just checking is faster in general. And then we also want to implement proof streaming. Right now, Lean's default way of handling files is to read them all at once. But if your proof is too large to store in memory, you can't even write it down in disk. Like say your proof is terabytes large, then you can't write it down. You have to stream the proof as you go. And so we have to slightly change the I/O API that we use in the Lean checker to handle proof streaming instead. And that is all that we have. If you're interested in more details, I'm happy to take questions via email, or you can look at the paper or any of the code. It's all open source. The paper is Verified Substitution Redundancy Checking. It appears in FMCAD 2024, and you can find it on my research website, crcodel.com/research. Thank you for your attention.